Good evening, everybody. My name is Lorenzo Perella, and this is Physics 116 with Clark Wellham. Today we're going over quiz number 2. Numbers 1 and number 4 in accordance with extra credit. The first problem states that we have both pipes of 1.0 meters in radius. The left pipe is 1.5 meters up, and the right pipe is 3 meters up. The left pipe has fluid pressure of 5 pascals and fluid as a rightward speed of 3 meters per second. Find the speed and pressure in the right pipe. Below this problem, what we have is a screenshot from a site that we can reach through the URL that's on the top in blue. We find that after we put in the variables that number 1 is given us, we see that the right pressure is 4.853 E5 pascals, and that the velocity in the rightward pipe is 3 meters per second as well. In order to prove this, what we use is Bernoulli's equation. Bernoulli's equation states that the first pressure plus 1/2 of the density times the first velocity squared plus the density of the fluid times gravity times height 1 is equal to the second pressure plus 1/2 of the density of the liquid velocity 2 squared plus density of that liquid times gravity times height 2. Now, as you can see, all this is supposed to work out with the first pressure being 5 pascals. Now, first we have to do is confirm that we know that the velocity doesn't change. In order to do this, we have to calculate the flow rate. The flow rate of Q1 to Q2 is that the area of 1, which being the radius squared times pi times the velocity of the left pipe, is equal to the area of the right pipe times the velocity of the right pipe. And since we know that the radius does not change from left to right, both velocities have to be the same. Thus, velocity 2 is 3 meters per second. Now, we apply this back to Bernoulli's equation. And once we have it all settled out, what we do is 519,200 units minus 4,500 minus 29,400, which equals 485,300 pascals. And this agrees to our visual that we got before in the simulation. Now we move on to number 4. This one's extra credit. So in this one, here's the numbers, but first let's go over the problem. Okay, so the student puts a straw vertically into a glass of water. They blow hard horizontally over the top of the water. Water rises up 2 centimeters in the straw above the level in the glass. Now we need to find what the speed of the air the student is blowing at. Now to do this, our professor, who is a great professor by the way, gave us the hint that in this problem we need to use Bernoulli's equation separately for both the air and H2O, because even though it is a gas, air is still a fluid because it moves fluidly. And that first, we need to use Bernoulli's equation in order to find the change in air pressure for the speed of the air blown over the straw. And then we need to do the same thing for the water. So first, we look up the density of air to be 1.225 kilograms per meters cubed. And we already know from our first equation that the density of water is 1.0 E3 kilograms per meters cubed. Now we apply this to Bernoulli's equation, and knowing that the initial height and velocity are 0, and we use atmospheric pressure because we're not using anything above or below sea level, we use 1.01 times 10 to the 5 newtons per meter second, which is the same as pascals, equals pressure 2 plus 1/2 of 1.225 kilograms per meters cubed times velocity 2 squared plus 1.225 kilograms meters squared times 2.0 e minus 2 meters, which is times 9.8 meters per second. It should be noted that centimeters have been converted to meters. And from there, we see that the second pressure is equal to the first pressure minus each part on the right hand of the equation. Now we use Bernoulli's equation for H2O. We know that water is not moving in a flow like a number 1. So this is a static fluid. And by doing so, we can see that the pressure plus density, gravity, and height 2 is equal to P1. And we see it like this because the water level is lower in the second part of the experiment relative to the straw. And from there, we find take the atmospheric pressure minus 1,000 times 9.8 meters per second, and 1,000 is the kilograms density, and then the same height as before. We get a new pressure of 1.00804 E5 newtons per meter squared. Now we apply this value back to the first application of Bernoulli's equation. From there, we see that new pressure is equal to the atmospheric pressure minus the value that we get from taking the density of air times the height times gravity, and then minus that by 1/2 of so forth and so forth. And then in order to make this work out, what we do is then move the larger value, because even larger value, which is here, right around here, to be 1.0099759 minus 1.00804 E5. We find that difference to be 1.95 E2, which is roughly 195. And then we divide that by 0.6125, which we get a velocity 2 squared is equal to 319.608 meters per second. Then we find the square root of that, and our final answer is 17.88 meters per second relative to the system, which is fairly speaking because we can actually blow pretty hard. It's just we don't think of it that hard because, wind is hard to measure in anything. Thank you for taking the time to listen to me explain this. Hope you find it helpful, and you all have a wonderful evening. Thank you.